beyond pairwise beyond pairwise interactions, I would like to mention that Stefano's contributions to science and to society are multifaceted. Not only is he director of research at the CNR Institute of Complex Systems, but for example, what is less known, he was also scientific attaché at an Italian embassy. Stefano?
Grazie, thank you a lot. So initially, I thought to make the presentation like Charo this morning to the blackboard, but then I said, okay, let's mix some pictures. So it will be half-half, okay? Half slides, half that. So what we are going to do today is taking back from the last talk by Pietro, we will complicate a little bit the story. That is, we will put the interactions in terms of the Laplacian, plus also some dynamics, which is the internal dynamics of the nodes. Okay, so we have now a network. Each node is a dynamical system, plus there is this interaction. And we will, for example, take the problem of synchronization. Why synchronization is important? You see, synchronization is a very old problem in physics. It goes back to Christian Huygens. You know, the legend says that he was sick in the bed, and he was observing the behavior of two pendula, which were hanging at the same wooden bin. And what he observed for the first time is that no matter you prepare the initial condition of these two pendula, after a while, the two pendula start to behave like this, to synchronize. Actually, he called this anti-synchronization, because they were like this, an odd kind of sympathy. He called it sympathy, sympathetic behavior, or synchronization behavior. And he observed these dynamics taking place between the clock. Of course, the clock were similar, were hanging at the same wooden bin, so the wooden bin provide the coupling between these two, so the interaction between the two pendula, or the vibrations that were, and he understood, Huygens understood completely the fact that this setting of this synchronization of sympathetic behavior, which is a collective dynamics, was entirely due to the tiny forces that the two pendula were exchanging because of the fact that they were hanging at the same wooden bin. So he understood very well this mechanism. And today, of course, synchronization is important. For example, in networked system, in animal behavior. No, the flocks, the birds are synchronizing their velocities while they're moving, or the animals. The brain, synchronization in the brain is a very fundamental phenomenon. When synchronization occurs in the brain at large scale, it's a pathological state because it's epilepsy. When synchronization instead occurs in the brain at small scales, is normal behavior, the normal functioning of the brain, where different parts of the brain are simultaneously in parallel carrying out different functions, okay? People are discussing about, is there a unique climate system in the world? So what you see in different regions is the fruits of some collective phenomena of synchronization around the world. But you know, also in man-made systems in the internet, if you like, you will clap. Clapping is a synchronization phenomenon because you have to synchronize the phase, otherwise you will never listen something collectively and wrong. Financial market is a clear kind of synchronization when you have a crisis and all the markets collapse together or all the markets raise up together. You know, power grid. It's important, a very important synchronization problem because you have to maintain, 50 hertz frequency in the power you distribute in the system. So you need to synchronize the phase of each power plant because otherwise you can have destructive effect, and so on. Another very famous synchronization phenomenon is the moon. Actually, when you see the moon, you see the same phase of the moon. Why? Because the rotation period and the revolution period of the moon have completely synchronized. Of course, this was not like this when the moon was formed. When the moon was formed, the core of the moon was liquid, not solid like now. Now it's a rock. It's a complete rock. It has no magnetic field. But inside the moon, in the past, it was fluid. So the interaction between moon and earth, produced internal waves, which, synchronized perfectly the rotation and revolution period. Then the moon solidified. Now it's a rock, so it cannot change anymore the rotation. And then you see the same face. So this is a clear case. So we want to study what? We want to study a big ensemble of dynamical systems which are coupled with a structure like a network of connections, how they can synchronize. And in particular, what can be the effects of higher order interactions on synchronization. So what I'm going to do, and I will leave you with this figure, what I'm going to do is, first I will describe to you the most elegant result that was obtained in synchronization in network, which is the master stability function. And then we will discuss how this can be extended to higher order interactions, which are the effects of higher order interactions. So, normally, when you describe synchronization, you take a control parameter, which is the coupling strength. In each connection of the network, you imagine to have a coupling strength. And this is your control parameter. And then you define an order parameter. So you have the unsynchronized phase here, when the coupling is very small, each node is independent with the other, so there is no order in the system. This is the unsynchronized phase, and this is the synchronized phase. When the control parameter is sufficiently high, all the nodes is going up and down together, like the pendula in the case of Christian Huygens. So, in order to study this, we have to approach this problem, then I will write again. So we imagine, in a generic case, you see, that each node of the network is a dynamical system, so it's represented by a vector xi of dimension m variables. This vector xi evolve in time, this is derivative with respect to time, with a function fxi, which describes the kind of system that you have. So this function fxi can be the Lorentz system, the Rössler system, the Fitsunagumo system, whatever you want. Plus a coupling, which is the same kind of coupling that was described by Pietro today. That is, you have the coupling strength, sigma, then you have the sum over all the elements of the network. Here is the elements of the adiacency matrix times a diffusive coupling of some function h. So practically what you say is, I have an identical system. Why identical? Because this function f does not contain the subscript I. So all the nodes are identical. And we need to make this assumption to have some generic result. Then I have a coupling. This matrix here encodes the structure of the connections. And then I imagine that I have an output function. So my system speaks to each other by means of the function h. And I have diffusion in the function h. That's all. Now, I write this because it's the simplest form, but in fact, I can anticipate to you that the same results are valid for whatever kind of coupling. They're not limited to this kind of coupling. The only limitation is that the coupling must be synchronization non-invasive. That is, the coupling should be 0 when the systems are synchronized. So you can have a generic function here of xj, xi, such that f of xx equal to 0. Not necessarily the difference. But why I put the difference? Because as Pietro has shown today, you immediately can rewrite the system by means of the Laplacian. The Laplacian matrix. So you have xi dot, derivative in time, fxi minus sigma, and here you put the Laplacian, which is exactly the same matrix that Pietro has introduced this morning. With the properties that you already know. For example, that is a matrix with 0 row sum property. Okay, so all the rest is written here, and now I proceed step by step on the blackboard. So I have these equations. Let me write. I have xi dot f xi minus sigma sum j 1n Laplacian ij h xj. Okay? The function f is obviously from Rm to Rm. The function h is obviously Rm to Rm. And now, which are the ingredients of the cake? You have 3 ingredients. The one is the dynamical ingredients, is what you put in a node, which system is evolving in the node, and how they are connected, how they speak to each other. This is the 2 ingredients of the dynamics. And then there is the ingredient of the structure that, as Pietro said, is entirely put here. Okay? So now the first step is, and I go here, to show the following, that the synchronized solution exists and is invariant. What does it mean, invariant? Invariant means that when I change the coupling strength, my parameter, sigma, the solution is the same. And the only thing that this fellow is doing is changing the stability of the solution. Now, the solution is x1 as a function of time equal to x2 function of time equal to xn function of time equal to the synchronization solution, xs. This solution exists because, you see, if you plug this solution here, this does not depend on I, and this is 0 because of the 0 row sum solution. You know? So this is 0. So this solution exists for all values of sigma, because this is always 0. So this solution exists, and it's invariant. And obeys the fundamental question, the fundamental equation xs dot equal to if fxs. So the solution is all the nodes in the network repeats the same dynamics of a single node. They're all synchronized. Okay? So now what you have to do, since this solution exists for all possible values of the coupling strength sigma, is studying the stability of this solution as a function of sigma. When this is stable, when this is unstable. And in order to do this, what you do is, what you do normally. So you define sorry. You define error state, delta xi t is xi t minus this solution. So how each node deviates from the solution. You plug into this equation and you linearize, and you take the first order in the linearized equation. What you obtain is this. You see delta xi dot comes from here. You will have the Jacobian of this function f calculated in the solution xs times delta xi. This is the first term coming from here. And then you have minus sigma, sum j 1n, Laplacian ij. Then you have the Jacobian of function h, calculated again in the solution, times delta xj. And you have one of such linearized equation per node. So each node has its m-dimensional linear equation. Remember, this is m-dimensional. This is the m-dimensional nonlinear equation which defines the dynamics of a single node. And this is the m-dimensional linear equation that defines how each node deviates from this dynamics. Okay? Quindi, this is everything clear. And now let me write this in a more compact way. That is, I take a big vector, big error vector, which is delta x1, delta x2, delta x3, delta xn. So I put the first m components at the delta x1, second n components delta x2, and I write this just in compact form, like this. Delta x dot okay. Here I have the identity matrix N, direct product with JF, XS, minus sigma L, JH, XS. And this is just compacting everything in a unique equation. It's nothing but this. You have it here. So this is delta x dot, the big error, and this is the kernel which evolve delta x. And now what I'm going to do is to use what Pietro said about the Laplacian. In particular, the fact that the Laplacian is a zero-sum matrix, and I also imagine, for the time being, that it's symmetric. So we are speaking of unweighted network. Once again, that's not important, but it's simpler, because in this case we can use eigenvalues and eigenvectors which are real. So this is zero-row sum, it's symmetrics. You know, being symmetric is always diagonalizable. And then we look to the eigenvalues and the eigenvector of this matrix. In particular, you learned this morning that the Laplacian has the first eigenvalue equal to 0. Comes from the zero-row sum. And this eigenvalue corresponds to an associated eigenvector, which is the unitary eigenvector, this one. 1 divided the square root of n, 1, 1, 1, 1, 1, transverse. But now look, what is this eigenvector? You have a very huge phase space, because you have m times n variables in this equation. This eigenvector is the hyperdiagonal of this phase space, because all the components are equal. So this eigenvector is exactly the synchronization solution, where all the xi are equal. Now, what I want to study the stability of this solution. So what I want is that this solution be attractive in all possible perpendicular directions. Because if it is attractive in all possible perpendicular direction, it means that when my trajectory visits closely the solution, it gets trapped to this solution. Okay? But then, if one direction, if my solution is V1, the space which is perpendicular to V1 is the one generated by V2 Vn. Because you know that a symmetric matrix has the property that the eigenvector form an orthogonal basis. So I have a basis, one eigenvector is my solution, all possible directions which are perpendicular to my solution are those that corresponds to the other eigenvectors. Okay? So what I have to do, I have to ensure that in all directions that corresponds to the other eigenvectors of the Laplacian, I'm contractive. If I ensure this, my solution is globally stable. This is clear, no? If you something... So, this is written here. Since this corresponds to the synchronization manifold, all the other eigenvectors Vi of the Laplacian form a basis of the space tangent to the synchronization manifold. Now what I do? I take this big vector here, this delta x vector, and I write as a combination of the basis Vi, that is, as a combination of the basis of those vectors which diagonalizes the Laplacian. And this I can always do because this is a basis. So this delta x will be the sum over some of this Vi, direct product with some coefficient. These are m-dimensional coefficients, xi, which are the coefficients of delta x along each eigenmodes defined by the eigenvectors. So I take this, I substitute over here, and then I take the scalar product left and right by each one of my Vi. And I obtain equations for what? For these coefficients Zi. Correct? Because I have a basis, an orthonormal basis, so Vi Vj is the scalar product is 0 except when Vi I equal to j. I obtain, therefore, this equation. Let me write this equation here. I obtain that Xi, or Xj, what is written there? Xj, okay, is equal to no, sorry, Xi. Here I have Jf xs. Then the only difference is then when I apply to the Laplacian, here I will have the appearance of the corresponding eigenvalue, lambda I. So here I will have minus sigma lambda I jh xs. Okay? And now the most important idea is this. I have the Jacobian of the function f and the Jacobian of the function h. These are the dynamical part of the equations. And I have the structure of the network, which is encoded in the different values of the eigenvalues. Now, what happens if you look at this equation? These are variational equations in the sense that the derivative of xi depends only on xi times this stuff. And this stuff depends on I only here. So if I take two i's, I prime, the only difference that in I will have lambda I, in the other I will have lambda I prime. And now the genius idea of two guys in the 90s, that was Lou Pecora, basically, was this allows me to disentangle the structure and the function. Why? Because what I do is I define here one parameter nu equals sigma lambda. I substitute this parameter here, and I study the generic parametric equation xi jf minus nu jh xi. That is, I do this. jf minus nu jh xi. This way, I've completely separated dynamics from function. Why? Because this equation, you see, depends only on the dynamics. jf, jh, and my nu, which is a parameter. Then I will find some property of the equation. I want, if I have a specific, if I have a specific network, specific structure, what I have to do is just to read this equation for the specific value of the eigenvalues of that network. So the idea is I have now one unique equation, which is m-dimensional nonlinear equation which defines my trajectory xs. And then I have one unique m-dimensional parametric linear equation, which is this. I calculate the maximum Lyapunov exponent of this equation as a function of nu, which is the maximum contraction expansion rate that you have. And this is a function of nu. And why it's a stability function? Simply because I have to read the value of this function at the point corresponding to the eigenvalues of my structure. So in practice, if you give me one system and one function h, you tell me, I want to simulate a Rössler system with this specific output function h, I tell you immediately this function. And this tells that this specific system with this specific output function, the way you have to connect it in order to synchronize or not. You understand? In particular, if you want the synchronization to be stable, you have to have a structure such that the value of the function in all those points is negative, because you have contraction. So, now, what is important is, if my function f is a complicated system, a chaotic system, the master stability function must start here for nu equal to 0 at a positive number. Why? Because we already saw before that nu equal to 0 means lambda is equal to 0. So when nu equal to 0, you're measuring the maximum Lyapunov exponent of the single isolated system. If the single isolated system is chaotic, by definition, this is a positive number. So my function here start at nu equal to 0 at some positive number. Then, whatever function you choose, whatever output function you choose, you have only three possibilities. Class 1 systems those for which this master stability function does not intercept the x-axis. I don't care if it is like this or like this, but there's no intersection. Therefore, these systems finish. They will never synchronize. No matter how you couple them, you can couple any way you want. There's no structure that can make this synchronization stable. Because for whatever values you read this function, you will have instability in all directions perpendicular to your solution. So, problem finished. If you have a system here, you know the system will never synchronize, no matter how you connect. It's a very powerful prediction. Then you have class 2 systems. Class 2 systems are those for which there's one interception, only one interception with the x-axis. And I call this interception nu star. So it may be like this, maybe like this, whatever, but it has one interception. The important point is the interception. Now, what happens in class 2? In class 2 system is the opposite of class 1. You can always synchronize. Why you can always synchronize? Because this axis, I remind you, is sigma lambda. So if you increase the sigma, at a given point, the eigenvalue 0 will remain 0 for all sigma. All the other eigenvalue will grow until they cross all this point. They will cross this point when this isn't sigma. This is the coupling strength. D times the second smallest eigenvalue, because they are ordered by sides, is larger than this. Then the third will be larger, the fourth larger, blah, blah, blah. So when this happens, in all directions perpendicular to your solution, you have a negative value. And so you're stable. So in class 2 system, what is very important is the synchronization threshold is, this doesn't work, the synchronization threshold is proportional, is sigma critical equal nu star divided by lambda 2. So what matters is just the second smallest eigenvalue of the Laplacian. And this morning you have learned that this is the connectivity, the algebraic connectivity of the network. You want a system, I give you one system, one dynamical system, one output function, you measure that it's class 2. Then if you want to synchronize easier, you just increase lambda 2. Increase the connectivity of this network. The more you increase, the less is the value of the threshold for synchronization. Okay? But in any case, if you are free of, in Spanish is darle al gatillo, if you are free of, increasing sigma as you wish, you will always synchronize, before or after. Then there is class 3. Okay, doesn't work anymore. No, the laser has no battery. In class 3, you have two interceptions of the x-axis. See? You have a V-shaped solution. Nu 1 star, nu 2 star. Now what you have to do is that all the spectrum of your Laplacian multiplied by the same sigma, all these values should stay in between nu 1 star and nu 2 star. So you don't have one condition, but you have two conditions. You have again that the coupling strength times the second smallest must be larger than nu 1 star, but with the same d or same sigma, the largest eigenvalue of the times the same sigma should be smaller than the other. Otherwise, you will have one direction of the phase space which is unstable. Okay, so class 3 systems are those for which you can, depends on how you connect them, you can synchronize or not synchronize, because it depends on the spectrum. So you see, this is very, very general, because given any dynamical system and any output function, it immediately gives you the condition for synchronization. And it can help, in fact, controllers to say, I want to have a network which is best synchronized. If I am in class 2, it's sufficient to increase lambda 2. It's a criterion. If I am in class 3, what I have to do, I have to compact the spectrum. Because the more I compact the spectrum, the larger is the chance that when I multiply the spectrum times one scalar, that is the coupling strength, it will fall entirely in the stability region. You know, and there have been thousands of things like this. Okay, so this is the situation of one network. Now, what happens when I consider either hypernetworks or multi-layer networks? And here I need to write things. So first of all, I have to tell you that this formalism of the mass stability function is 24, 25 years old. And it's been extended in thousands of cases. For example, the first case has been studying what happens when the systems are not identical. Because, you know, if you measure real system, you never have identical system. So what happens, for example, if you have the same system but with parameters which are distributed in a given distribution? It has been shown that the prediction of these are very robust when the variation of the parameter is not too big. That is, when the distribution of your parameter is sort of Gaussian or very well defined. Then it was extended to other coupling functions, that is, to various functions which are synchronization non-invasive but not diffusive. So what does it mean, multi-layer network? Multi-layer network means that I have my nodes and many layers of interactions. So I have equations like this. Then I have layer 1 of interaction when I have sigma 1, sum j1n, Laplacian ij1, which tells me how they are connected in layer 1, times a function, let me call it g1 of xi, xj. Then I have minus sigma 2, same thing with here 2, 2. Minus sigma 3, minus 6. So I have many layers of interaction. Each layer is a different network, so I have a different Laplacian. And each layer corresponds maybe to a different coupling function. Why not? So I have, if you want to write it in a compact way, sum k1m sigma k k k. Okay? Sorry? Sigma k should be inside, yes. True. So this is the case of multi-layer, which I can have same node, same dynamical system, and different layers of interactions. So this is multi-layer. Then, what about higher order? Hypergraph. I will have equations like this. Again, I have my nodes. Then I have interactions of order 2, of order 3, of order 4, of order 5, of order m. So I will have here minus sigma, let me call it 2, for sum j1n, L ij 2, g2, xi, xj. And this is something that is depicting me the interaction that I have order 2, the pairwise interactions. Then I have minus sigma 3, sum j equal 1n, sum k equal 1n, lijk 3, g3, xi, xj, xk. And this is depicting me what happens in each hyperlink of order 3. Then I have another term. Then I imagine that I have, so to say, a maximal order of interaction equal to m. So I have minus sigma m, sum of j1, j2, I, j1, j2, jm minus 1, L, I, j1, j2, jm minus 1, g, m, xi, xj1, xj2, xjm minus 1. So each order of interaction corresponds to a specific function g of m variables. Okay, well, one variable is I, because I'm considering node I. All the other variables are the variables that are running around. And the structure of the corresponding eigen, or the corresponding, these are, how you call it, this one, K uniform, no? These are K uniform hypergraphs are included in the tensor. You say that it's not a tensor, but it's a tensor, the corresponding tensor. Sorry? The sum is J1. J1, Jm minus 1. Okay? So the sum is various sum. Okay, I'm not going into the details, but what I'm telling you is the following. You can, if you want to have a complete discussion, there are two very important papers that were demonstrated the extension of the master to these cases. What I can tell you is, here it's easy to understand that each layer corresponds to a different Laplacian. And these Laplacian are all matrices. So you have different networks. This is the sum of different networks, so it's like that you have different Laplacians. In this case, in higher order, you can prove, not easily, that is, it takes some page of algebra, that each order of the interaction, that is, each one of this order here, can be mapped into a generalized Laplacian equations, where the degree that this morning he introduced and the generalized degree appears in some with factorial stuff. So, since this is the sum of things, in the linearized equation, you are at the end making linearization, you have the sum of different cores. And now the point is, you are having here the sum of matrices, each one of them being zero-row sum. So these matrices are all of them sharing the fact that one eigenvalue is 0 and the corresponding eigenvector is 1, 1, 1, 1, 1. So each of these matrices, the Laplacian here and the generalized Laplacian there, they have the same eigenvalue, 0, and the same eigenvector, 1, 1, 1, 1, 1. But now, what about the other eigenvectors? The other eigenvectors are equal only if the matrices are commuting. If you take, in general, generic networks or generic order or generic layer of interaction, there's no reason why they should commute. Actually, the general case that they don't commute. So what happens? It happens that all of them have the 1, 1, 1 solution. But then you have m different bases for the tangent space. All of them are a basis of the tangent space, but they're different. One will be the basis, for example, which diagonalizes the first. Then you will have a different basis, which is the one diagonalizes the second, and so on and so forth. So what is the point here? Is that you can always say that you have always a way of representing the tangent space to this solution. But here you don't have one, you have m. And so the trick here is that you choose one of them. You can choose any one because each one of them is a basis. And you transform all the other bases into this one by means of unitary transformation. So, when you will transform, you will adopt this basis. For example, let's suppose, for simplicity, you adopt the base for lambda 2 for the typical Laplacian. Then, when you do exactly the same stuff here, you consider the vector delta x. Now, the vector delta x will be, again, a combination of these bases. When you plug here, in the equation here, and you make the scalar product, this basis will only diagonalize one Laplacian and not the others. So you will never end up with a variational equation in which each of these coefficient xi, xi will depend only on xi. But you will have this core for the specific matrix of which you have chosen the basis, plus here a coupling with all other possible xj with the coefficients that map one basis into the other. But these are known, because you know the different layers, so you know the transformation from one basis to the other basis. These are completely known, but the only difference is that you don't get a set of unique equations. So you cannot parameterize anymore with a unique parameter, but you have to study one equation, which is the m-dimensional nonlinear equation giving you the solution, and then you will end up with a system of n-1 linear coupled equation. And now the coefficients are all known. So still, you can calculate the maximum Lyapunov exponent of this equation, and see how this maximum Lyapunov exponent depends on the various parameters, which in this case are the sigma k, and in this case are the sigma 2, sigma 3, sigma 4, sigma 5. So you don't have anymore a unique parameter nu, but you will have many parameters, sigma 2, sigma 3, sigma 4, sigma 5, and regions or hyperregions of this where you have stability or instability of your solution. It's clear? If you want the details, I repeat, it will take hours to, but you can go and read this. So, since I have still half an hour, but I don't want to bother too much you, because you are a little bit tired, I want just to tell you a nice application of this, which is cluster synchronization. So going back to here, what I told you since the beginning, that I have these two phases, the unsynchronized phase and the synchronized phase. And I want to study the transition between these two, how I'm passing from one to another. This phase, everybody is from physics here. Everybody from physics? No, from mathematics, then engineering, what? Computer science, mathematics, physics. Data science, okay. So, I now adopt a physical language. This state here, this phase, is the phase where all the systems are unsynchronized. So there's no correlation between the systems, zero. This is equivalent to a gas, a Boltzmann gas, where all particles are independent to the other. So this is, I will call it gas phase. The other phase, instead, is a solid. It's a perfect order. It's like a crystal, so it's a solid. So this is equivalent to a phase transition from a gas to a solid. I don't remember how it's called in physics, depositation or something like this. The opposite I know is sublimation, but the going brinamento, brining, something, brinamento. So this is brinamento, this is sublimation. Sublimation is what happened to you when you go outside here, that you pass immediately from solid to gas, because it's very hot. You see? Now, there are two ways to do this. One is by means of a first-order-like equation. That is, when this transition is discontinuous. So imagine that you are in the phase 0, in the gas, then you continue in the gas, and then you jump to the solid. And then you may have hysteresis, that is, you can start from the solid, going down, you jump down, but at a different value of the coupling, you can have this. And you understand that if you do this, which is called, by the way, explosive synchronization, you can have this, you don't have intermediate phases. So either you are a gas or you are a solid. There's no intermediate configuration in the network. And moreover, I told you that you may have hysteresis. That means this may be a non-reversible process. That is, this you go up, but here you are non-reversible. Okay? Or the most common case is this one, where you have a second-order-like transition. The transition is continuous, is smooth, and is reversible. What means reversible? You start from the gas, you increase the control parameter, and you synchronize. But you can do the opposite. You start from the synchronized solution, you decrease the parameter, and you make exactly the same path. And now the interesting point is, you know, this is a stupid state because it's a gas, a Boltzmann gas. You cannot make prediction. This is also a stupid state because everything is repeating the same. No? The most interesting states is here in the middle. How can I define the middle? The middle is a situation where I have mixed phase. Now, this mixed phase corresponds to clusters, that is, to specific nodes, a specific group of nodes, which synchronize among them independently on the rest of the network. So I can have not a synchronization in the sense that all the solution is synchronized, but only specific group of nodes. And so the question is, how can I describe? I can now predict which one of these nodes will be synchronized. Can I predict when they will synchronize, the sequence at which they synchronize, blah, blah, blah. And the idea is this. I describe to you the stability of the synchronized solution, that is the stability of the solid phase. I can repeat exactly the same thing, but now not around this solution, which is everything is synchronized, but around a cluster solution. That's only a group is synchronized and the other is not. I can do exactly the same thing. And I then end up exactly with the same linear equation. This one. With only one difference. That now the solution S is not this. Now the solution S is this, perturbed by the fact that the sum of the nodes in the cluster is connected with some node which is not synchronized to them. Because you have a group of nodes which synchronize, and these groups are connected with other nodes who are not synchronized. And this provides here a perturbation. The fact that your trajectory around which you have to calculate the Jacobians is not the trajectory of a single system repeated n times, but it's perturbed around. So this means that for each of the coupling, you will have to find, in principle, a different curve, a different mass stability function. But now let me make a very rough approximation. Since I'm a physicist, I can do approximations. Zero order approximation. Let's suppose that these perturbations are small, very small, and indeed they are. You will see a posteriori that they are. So let me imagine that as a very rough approximation, I consider this perturbation to be zero. So I refer to a unique mass stability function for all possible clusters, which is not true, I repeat, but it's a very rough approximation. Now, if this is true, well, no, if this is true, if I adopt this approximation, what happens? Class 1. There's no synchronization, there's no cluster synchronization, there's nothing. Finish the job. Class 2. So what happens if I am, okay, if I am here, if I already passed the threshold, I am in the solid phase. But what happens when I am here? When the coupling is not yet that of the solid phase. It will happen that some eigenvalues multiplied by sigma will stay in this area, and some other will stay in this other area. So I will have my solution, and the tangent space is, I can factorize like the product of one completely expanding state, which is the one generated by the eigenvector whose eigenvalue stays here, times one completely contractive one, which is the one generated by those eigenvectors whose eigenvalues are staying there. No, my space is the product of these two spaces. But now look what happens. I know the order at which the eigenvalues pass this threshold. Because suppose that I start for a very, very small sigma, where all the spectrum is here. And I increase sigma. The first eigenvalue which will pass the threshold is lambda n. Then I will have lambda n minus 1. Then I will have lambda n minus 2. So the different eigenvalues will pass from unstable to stable in the inverse order of their size. So at each value of sigma, I know this completely contractive subspace, how it is generated, because I take the eigenvector that corresponds to those eigenvalues. So I know. And so what I'm doing since now is, let me concentrate for each value of sigma in the transition only on the subspace that has as orthogonal basis the set of eigenvector vi, whose corresponding lambda I multiplied by sigma of d have already crossed the stability threshold. Td will always, for all values of d, contain only contractive directions. And now I go to this, which is the key finding of this. I need to make a definition. Definition of a spectral localized block. So, look, I take a subset of k minus 1 eigenvectors of the Laplacian, and this set is defined by k indices, I1, Ik. And I say that this subset, consisting of k minus 1 eigenvector, forms a spectral block localized at the nodes I1, Ik, because the indices are the indices of the nodes, if each eigenvector that belongs to this set has all entries except I1, Ik equal to 0. So it's an eigenvector with component 0 everywhere except in those nodes. So it's localized. In this sense, it's localized. And all other eigenvector which does not belong to the subset, since they have to have a scalar product equal to 0 to this stuff, must have the entries I1, Ik all equal. Not necessarily 0, but have to be equal. Otherwise, they never. Okay? So this is the definition. And now I can prove, well, I proved this theorem. This is the most fundamental theorem about cluster synchronization, because it tells you the following. The two following statements are equivalent. So it means that if and only if. So let me tell you the statement 1. I have k nodes of my network. K nodes of my network. These k nodes are defined by the indices I1, Ik. Okay, that's k nodes. And they belong to a cluster which have the following property. These nodes have the same connections with the same weights with all other nodes of the network. It means that if I take any pair of indices PQ inside I1, Ik and J outside I1, Ik, the element Pj and Qj of the Laplacian are the same. This is statement number 1. But what does it mean, this statement? It means that these k nodes are indistinguishable by any other node in the network. But much more important, it means that these k nodes receive the same input from the rest of the network, independently on the state of the network, because they are equally connected to the rest of the network. So whatever is the state of the network, each one of these k nodes receives the same input from the rest of the network. So it means same input equals same output. These k nodes are potentially synchronizable, independently on the state of all other nodes in the network. So statement number one says that these nodes are potential cluster that can synchronize independently on the rest of the network because they receive the same input. They are forced by the same input. So this is statement number one. And this is equivalent to statement number two. There is a spectral block S I1 Ik made of k minus 1 Laplacian eigenvectors localized in I1 Ik. So this theorem says that all possible potential clusters that you have corresponds to blocks of eigenvectors which are localized in the corresponding indices of the nodes. And now the trick is done, because what happens when they will be localized, these eigenvectors, and the localization will occur inside the fully contractive subspace, the corresponding cluster will be stable. Understand? So, I know that when I increase the coupling strength, first lambda n minus 1, I know how this contractive subspace is formed. When this contractive subspace will include a block of eigenvectors which are localized there, the corresponding cluster will appear as a stable cluster, because it means that this is localized, so that these eigenvectors are only there, and this only there means you are completely contractive. So how you do this? For the good of the mathematician, you take for each eigenvalue you construct, you compare the components of this eigenvalue in a matrix, then you take a sequence of matrices which is in the same order, n minus 1, n minus 2. So you follow the order of the eigenvalues, and you add one component more, and then you take these matrices, you sum, and you see that this is nothing but taking the matrix of all eigenvectors, taking the rows as vectors, making the difference, making the square, and limiting the square to n minus 1, summing back here. And this means that if you consider any of such matrices, the maximum entry is 2, because the maximum entry is when you have two vectors which have norm 1. The maximum entry is when they are perpendicular, when they are orthogonal. So you have square root of 2 is the difference, the square is 2. And so the game is done, because what I have to do is just cook the cake. Take a network, consider the Laplacian, extract the eigenvalues, order them in size, extract the corresponding eigenvectors. This is 1 picosecond of CPU. Then calculate the matrices and what I'm saying. Then inspect the sequence of matrices in the same order with which the Laplacian eigenvalues crosses the critical value. And when for the first time I see a 2 in the sequence, it means that I have vectors with orthogonalized there, so they have to be localized. No? And so I read the ij value there, and I know which are the clusters that are going to be formed. So, look, I make you an example to understand better. This is an all-to-all connected network in which I prepared the weight. So it's weighted. So as the statement 1 of the theorem is valid only for these 3 clusters. So, for example, take 7, 8, 9, 10. See, 7 with 4 is 0, 5 to 9. 10 with 4, 0, 5 to 9. 9 with 4, 0, 5 to 9. 8 with 4, 0, 5 to 9. So they are equally connected to the rest of the network. No matter how they are connected among them, but they are equally connected to the rest of the network. So these 3 clusters are the only potential cluster that I see because of the theorem. And now what I do, I have 10 nodes, I have 10 eigenvalues, 10 matrices, and I inspect my matrices in the order in which the eigenvalue passed the threshold. So first S10, S9, S8, S7, in the inverse order. Go. S10, do you see something equal to 2 here? No. There's no 2's here. So we go to S9. Something equal to 2? No. S8. Wow. Wow. First prediction. When the coupling strength of my system sigma is the new star famous of the mass stability function divided by this lambda 8, please. No, 2 is synonymous of orthogonalization. But if they are orthogonal, it means that all the other components have to be 0 because they so they're localized. So first prediction, the first cluster I will see in the transition is 7, 8, 9, 10. I just read there. 7, 8, 9, 10. And this cluster will form exactly when the coupling strength sigma is nu star divided by lambda 8. So I have a prediction on the value of coupling strength which makes this cluster appear. Now, these are already orthogonal. So when I add the new component, it will remain 2. So now I continue and I say, are there additional 2? So S7, do you see additional 2? No. S6, additional 2? No. Here, you see, it's very similar. Almost, but not 2. S5, wow. So second prediction, when you have a coupling strength sigma such that is nu star divided by lambda 5, nodes 4, 5, 6 will join the cluster 7, 8, 9, 10. Other situation would have been if this is 2 block, then you have 2 different clusters. But here you have unique block, so it means that the other joins this. Then you continue. S4, S4. Nothing more, and then you have the solid phase, L2. Yeah, there is node 1 and 2. But this is a mistake because it's almost 2. It's not 2. Almost 2. This is 2, really. So you see that just without, and this is the important point, is this is independent on the dynamics. So this depends only on the structure. Which means that if you look if you have a system and you look at the transition of the Rössler or the Lorentz or whatever system, it will always show the same sequence of the same clusters. Yes. Now this is the prediction. Without any simulation, you just make Laplace say, this is the first event in the transition, this cluster. Then when the eigenvalue of mu star divided by this will join this, and that whole cluster joins. And then you make simulation. Take the Lorentz system, the Rösler system, and you plot the synchronization error corresponding to each one of the three clusters. It's the difference between the variables summed all on the nodes of the cluster. You see, Lorentz system, this is the coupling strength. The first that's synchronized, that is, the difference goes to 0, is 10, 9, 8, 7. And it's synchronized exactly at D1, the value that you predicted from there. Then the second that's synchronized, and join this, is 6, 5, 4. Once again, same value that you predicted. So you see that the hypothesis we made that we can refer to unique, even there is a perturbation, the perturbation is small. And then finally, all goes here. And this is a universal transition. That is, if you take this axis here, you divide this axis times 7.322, which is the new star in the case of the Lorentz. Then you multiply it by the new star of Rösler, you obtain this other axis. So basically, you have a transition which is independent on the dynamical system. So, in other words, what is the role of the dynamics? The role of the dynamics is fixing this new star. Because the mass stability function is a function that depends only on the dynamics. So the dynamics decides new star. Once the dynamics decide new star, all the other features of the transition are decided by the structure. You understand? And then you can prove with many node, blah, blah, blah. For example, here we made a simulation in which we consider not identical system, are these prediction maintained? For a while they're maintained, in the sense that you lose now the perfect prediction on the exact value where they are stable, but the sequence is the same. The yellow is always before the orange, and the orange is always before the red, and these things. So, to conclude, we have a very powerful tool now to approach whatever network of dynamical system. And this gives, under some approximation, very elegant and very powerful prediction on the stability, not only of the completely synchronized state, but on all possible clusters that you have in the synchronization. And this is the powerful stuff. Now, what is the step to do now? The step to do is try to see how much of this prediction are valid when I release the various approximations and the various hypotheses that I do in the master stability approach. The first one is identical system, but this is already more or less done. The most important one, and I think is the most important step to do, is what happens when the coupling functions are non-synchronization non-invasive. That is, they are synchronization invasive. Because, for example, in the brain, when the two neurons of the brain synchronize, the coupling function is not 0. Actually, the coupling function must not be 0, because otherwise the second neuron will not fire. So what happens, how much of this, and this is a very problematic point, because when these functions are not 0, it means the solution is not invariant. It means that when you change sigma, you not only change the stability property of the solution, but you change the solution itself. So that's a much more complicated problem that is still not solved. And so if you want to apply to this, it's very general. So you see, very generic problem, very elegant, but it still needs to be approached. That's all. This is also on traditional, and indeed I would start from traditional network before going to, yes, this is still an unsolved problem for traditional network, yes. Okay, I finished. Questions? When there's no questions, there are only two options. Either the class was fantastic or was horrible. There's no... Oh, one good question. So it's not horrible, the question. Which one, G function? This one? This one, yes. Okay, so this term here is the coupling that you have in each pairwise interaction. So node I is interacting with node J in all elements of the Laplacian matrix which are different than 0, because it means there is a connection. And they're interacting how? They can interact with the difference of the state, or in general, they can interact with the function of the two variables, xi, xj. For example, in the very celebrated Kuramoto model, just to make an example, Kuramoto this year won the Boltzmann medal. In the case of Kuramoto model, the coupling function is the sinus of the phase difference. But it's not the phase difference, it's the sinus of the phase difference. And you know that sinus A minus B is not A minus B. You know? So there's two different things. Sinus of A minus B is not a diffusive coupling. But it's 0 when A is equal to B. So you can have any function of xi, xj, which is 0 when xi is equal to xj. For example, take this function, xi square xj minus xj square xi. This cannot be written in a diffusive term. It's not something of xi minus something of xj, but it's 0 when xi is equal to xj. So this is much more general than a simple diffusive case. And this is G2. Then I have three-body interaction. And when a node is participating in a three-body interaction, what I have another coupling strength, maybe different than sigma 2, who knows? I have the terms which defined in this tensor, which tells me which hyper edge I have. And then I have a function of three variables, xi, xj, xk. No? And this function, once again, must be such, it is 0. For example, this function is 0 this function is 0 when xi is equal to xj is equal to xk. No? I have xi squared, sorry, here cube. Xi squared xj plus xj squared xi minus twice is k cubed. And this is not at all a diffusive function. So this can be a generic function of xi, xj, xk, which is 0 when xi equal to xj equal to xk. And then I have 4-body, and then 5-body, and 6-body. And for each one of this order, I will have a different function, which is function of more variable, of course, and which describe the kind of interaction that I have at different orders. Okay? Please. But in the case of Kuramoto, yes. But of course you can do. Of course you can do. But the mean field approximation normally is used when you don't have such elegant way. So here you have everything, without recurring to the mean field approximation, because everything comes from analytically. So why you should do an the point is that when you cannot do this anymore, like in the Kuramoto, then you adopt other things because you're stuck. Yes. No, no, I'm not saying that it doesn't matter. It's a little bit more complicated, of course. Yes, first of all, well, the simplest when you have a non-symmetric case, you can have two cases. Case number one, the matrix, I'm speaking about network now. The matrix is non-symmetric, but is still diagonalizable. Second case, the matrix is non-symmetric and is not diagonalizable. If the matrix is diagonalizable, nothing changes here, except the fact that this new parameter is complex. That is, you will have real part and imaginary part, and you will have to study, instead of having of studying, sorry, the maximum Lyapunov exponent as a function of nu, you will have the maximum Lyapunov exponent as a function of real part of nu and imaginary part of nu. Nothing changed. So you still have class 1, class 2, class 3. Class 1 is when it's never negative. Class 2 is when the region in the complex plane where is negative is unbounded. And the other one is when it's bounded. Here you can have the difference that you can play. You can have instabilities in the real part, but also instability in the imaginary parts. You have phase instability. You have many, many things. But conceptually, it's exactly the same. When instead your system is not diagonalizable, you can adopt Jordan representation. And we will talk about this tomorrow. So practically, you can show that in a Jordan representation, you have a cascade of problems. You have a cascade in which it's still important class 1, class 2, class 3. But when you are stable, so practically what happens is that you don't get equations like this, but you get an equation for C1 that only depends on C1. An equation for C2 that depends on C1 and on C2. Then C3, C1, C2. So what happens is that if this is negative, this kernel is negative for all of them, then you will have to wait a first transient time for C1 to go to 0. Then C2 will be decoupled from C1 because this goes to 0. And then it will go to 0 also because then if C1 and C2 will go to 0, then C3 so you have a cascade of transient time. So the stability issues is the same, but you have to wait a little bit more for the system to get stable. So you have a relaxation time which is different. I told you that it's not important because there is a solution, not because it's trivial. I mean, but you have, the solution exists. So that's not a problem. The big problem is this. Everything depends on the fact that you have an invariant solution. So everything depends on the fact that your coupling function must be 0 when you are in the synchronized state, which I repeat is not always the case. Of course, yes. You can have many more classes, you can have many more intersections, you can go down, up, down, up, down, up, down, up. But what's the point? The point is that you're looking to the first transition to synchronization. So you're looking when you start new from 0. So the first transition is either you have one or you lose after. Then if you have a third, you will have a system that first synchronizes, then desynchronizes, then resynchronizes, then redesynchronizes, But this is, just, you are now studying the first transition to synchronization. That's why you have only 3 classes. But in fact, you can have much more weird situations.